My name is Max Kenny. I am a 12th grader at Minnetonka High School, and this year my project will be a cyclocopter, uh, and it is currently
This
in
is
progress.
the Quad Cyclocopter project. My research investigates the aerodynamic design, mechanical implementation, and scalability of cycloidal rotor aircraft. The objective is to synthesize the current state of aerodynamic literature to engineer a functional medium-scale prototype, targeting a takeoff weight of roughly 3 to 5 kilograms, within a strict $900 budget. While the vast majority of modern UAVs utilize fixed-pitch screw propellers, this project pivots to the cycloidal rotor, a propulsion system that offers superior agility through the principle of instantaneous thrust vectoring. A cyclocopter is a vertical takeoff landing aircraft VTOL characterized by barrel-shaped propellers rotating around a horizontal axis. Unlike a standard quadcopter, which relies on differential motor speeds and must tilt its entire airframe to accelerate horizontally, a cyclocopter operates on a fundamentally different principle. It changes flight direction by altering the pitch angle of its blades at specific points in their rotation. This mechanism allows the aircraft to generate a net thrust vector in any direction, 360 degrees around the rotational axis, while the main fuselage remains entirely level. The decoupling of the fuselage orientation from the flight path allows for immediate seamless transitions between hovering forward flight and backward flight, rendering the vehicle significantly more maneuverable in complex 3D environments compared to conventional rotorcraft. The core of this agility lies in the mechanical assembly of the rotor cage. The system utilizes teardrop-shaped airfoils connected to a central hub via a pitching linkage. The thrust vectoring is achieved through eccentricity, which is controlled by offsetting the center of the control ring relative to the axis of rotation. Shifting this offset center mechanically forces the blades to oscillate. This oscillation is defined by two variables, magnitude and phase angle. The phase determines the thrust direction. For example, phasing the blade pitch to maximize the angle of attack at the top of the arc generates upward lift. Shifting that phase angle by 90 degrees directs it thrust downward. This requires a robust assembly of servos, pitch links, and pivoting blade struts to maintain structural integrity, managing dynamic aerodynamic loads. My experimental design is grounded on mainly three foundational studies. First, Benedict et al. 2016 established the feasibility of small-scale cyclocopters with an 800-gram vehicle. They demonstrated that a passive pitch mechanism could successfully achieve stable flight with 8 degrees of freedom. Crucially, they implemented a hybrid control strategy where pitch roll and yaw were managed entirely by differentially varying the thrust vectors of the 4 individual rotors. This eliminates the need for traditional control surfaces, confirming that the mechanical architecture is viable and serves as a baseline for my larger 3 to 5 kilogram prototype. Rami and Piscola 2019 provided the critical aerodynamic data for takeoff and landing, using advanced fluid dynamics simulations to analyze the rotor's behavior and ground effect. They found that cyclorotors generate a concentrated pile-like downwash flow when operating in close proximity to the ground, specifically at low altitudes like 2 meters. This flow obstruction creates a high pressure level that results in a positive ground effect. This phenomenon significantly enhances the total efficiency by providing a cushion of air for the aircraft. However, the data revealed that static operating schedules are inefficient. Optimal settings shifted from a 30-degree pitch at 200 RPM at 2 meters to a 40-degree pitch at 400 RPM at 5 meters. This necessitates an active control system to dynamically adjust these parameters during flight. Alter and Benedict 2022 addressed the physics of scalability, which is critical for my heavier build. They identified a fundamental conflict between aerodynamic and structural scaling. Aerodynamically, scaling up to 5 kilograms is favorable. As the rotor size increases, the Reynolds number improves from 1 times 10^5 to 5 million, resulting in higher force efficiency due to smoother airflow over the larger blades. However, structural scalability is a limitation. The weight of the blades increases disproportionately due to the square cube law. To counteract this, the study validates using specific material compositions, foam cores with carbon fiber skins and spars to minimize rotational inertia while maximizing stiffness. Applying these findings, this project targets the construction of a 3 to 5 kilogram functional prototype within a strict $900 budget. This medium scale category allows for less outdoor flight but requires significantly stronger components than those found in the literature. To address the structural challenges, I will use high-strength adhesives and composite materials similar to those referenced. The experimental phase will focus on airfoil optimization. I will be testing variations of the symmetrical NACA 0018 through 0023 airfoil profiles to determine which thickness to chord ratio provides optimal lift-to-drag performance for the specific Reynolds number regime. The entire assembly is currently being modeled and analyzed in Autodesk Fusion to simulate mechanical stresses and verify the geometry before physical fabrication begins. By synthesizing the findings from these 3 studies, I have established a robust design framework. First, I am adopting Benedict's validated architecture to ensure agility without excess weight. Second, I am integrating Rami's aerodynamic control logic. The flight controller will actively vary RPM and pitch, targeting 30 degrees at low altitudes, 45 degrees at higher, to exploit the pressure bubble for maximum lift efficiency. Finally, I'm adhering to Halder's material constraints by using carbon fiber composites to mitigate the weight penalties of scaling up to the 5 kilogram class. So at first, when I tried to design the cyclocopter, I couldn't find any previous people who have made the design before, so I had to look for CAD files, and I couldn't find many of those, but this is the first one I found. So this is the first one I found, and then I had to learn how to use Fusion 360 and how to manipulate rigid bodies in order to make the cyclocopter what I want. And now I not only know how to do that, but I find it fun to do so. So this was the initial design, and then I decided to modify it to this design. So basically, I removed all the propellers from it, and now I have this body, and then I made the body for this. But then eventually I had to get rid of this design. And then I have more designs of other things, such as a snap fit box that I was planning on putting here, but I decided that that's not as important. And eventually I realized that I need the exact materials that I will be using for building my project in my Fusion 360 in order for it to have any real value. So this is one of the motors I'll be using, and that's for rotating the propellers. And I will be using 20 kilogram servos for manipulating the center of rotation of the linkage mechanism, where all the linkage is attached to, and and the whole propeller rotates around. So this helps the cyclocopter steer, and it helps it maintain throttle, and it also helps it rotate its wings to direct thrust. And so, through research papers, I found out that these NACA 0018 wings were the best choice of wings for a higher scale design, at least in simulations, but I wanted to test that in real life. Okay, and then, so, I copied off that, but I followed Mobile Benedict's design where he cut out rectangular slats, and then that made the blade significantly lighter, and I will wrap this in mylar film just as Mobile Benedict did, and I will run a 6mm carbon fiber tube through each blade in order to secure it and to make it stiff, and also secure it to the outside propellers, the outside frames for the propellers. And then, well, I had to get all of the materials I would be using to build. So these are the bearings, some of the bearings I'll be using, and then so I found all of these through CAD files and CAD websites. So these are the servos, those are the shaft collars. These are some more bearings, and then that's not a screw. And these are some of the motors I'll be using. And then this is the frame I'll be using. So, and then my original plan was to have the rods for where the propeller spin on to go off diagonally, but then I realized that it would be more stable if I put it off the middle, like I did here. So this is the design I'm currently working on. So this is the 8mm steel rod where the cyclocopter will be rotating around. It'll be stationary, this rod will be stationary. And then these are the linkages with the threaded rods that are supposed to connect to the blades in order to steer them in direct thrust and throttle. And then this is a servo mechanism, and this is supposed to change the center of mass of rotation. So it's supposed to move around this bearing housing. There's a bearing inside that is attached to this linkage mechanism. And so what those servos will do is move the center of mass of this mechanism around. So as you can see, the center of rotation. So the center of rotation is right here at this point, but theoretically it can go anywhere around here. But I just realized that these linkages may cause some interference, so I need to update that, and then I need to complete the propellers, and then complete the rotation mechanism, as well as the linkage mechanism, and then I will simulate using dynamics, and then eventually I will build the cyclocopter in real life and test it in real life. But first I will test it in simulations, such as fluid dynamic simulations. But hopefully I will be able to demonstrate a working flying cyclocopter by a state competition if I qualify. But for the TCRSF competition, I will be displaying the simulation results for my cyclocopter, and I am still working on the model as of now. This is my progress.